Hey everybody, this is chapter 17, which is about thermodynamics. Wow, it's pretty fun stuff, really. And there's a couple of important new ideas that we're going to introduce in this video that I'm going to try to keep short. So if I go a little fast, make sure you pause and rewind and even use your textbook or the internet if you need or another resource. But hopefully we're going to get us over these first couple of ideas about what is spontaneity versus non-spontaneous, and what is the concept of entropy all about. So thermodynamics is the study of the relationship between heat and work, and it is one of the newest branches of the physical sciences. It's very important in physics and very important in chemistry. And unlike most of the main ideas that we cover in chemistry and physics in an introductory class like this, thermodynamics is relatively new, a little more than 100 years old. Spontaneity is this idea of whether something can happen by itself, whether a process could possibly take place unassisted, without any outside interference. And entropy we're going to learn about is a funky mathematical concept relating to the distribution of energy states within a system. And there's a simpler way to think about it, and that's mostly all you'll have to do. But just for fun, I'm going to give you a little bit of the deeper, more scientifically correct description of entropy. And then free energy we'll cover later. In the chapter and in a different video lecture. It's a thermodynamic function relating the heat change of a reaction, the enthalpy change, and the entropy change, or the change in the distributions of energy, whether or not the system becomes more disorderly or not, with the spontaneity of the reaction, whether or not it will happen. All right, so again, spontaneous versus non-spontaneous. I'm being a bit redundant here. If a process is spontaneous, then it is something that can happen. If a system, that means all of the chemicals in our case, usually, if they're left to themselves, then a process can take place, a chemical reaction could take place. You don't need any outside help to get the process going. And then a non-spontaneous process is one that cannot take place unless some outside influence disturbs the system. And we've covered equilibrium already before, so you should be able to guess that if a process is spontaneous, then the reverse process would be non-spontaneous, and vice versa. Gasoline spontaneously combines with oxygen, but it is unusual for oxygen and carbon dioxide to go back into octane, go back into gasoline. The unit that we covered earlier this year on kinetics told us a lot about chemical reactions and the rates of reactions, how fast a particular process might occur. And we talked about some reactions that happen very, very fast and some that are extremely, almost excruciatingly slow. The new idea that we're covering here, thermodynamics, doesn't tell us anything about the practicality of a reaction. It just tells us whether or not a reaction could happen, whether it is possible. So we know that gasoline and oxygen can combine and a combustion reaction can take place. But you can have a can of gasoline, sitting in your garage for 50 years and there's no fire. So why doesn't it react? Well, that has to do with the kinetics of the reaction and how much activation energy is required. So we don't get a sense for how practical a reaction is just by knowing if it's thermodynamically possible, if it is spontaneous. All right, thermodynamics, oh yeah, one too far there. Thermodynamics, again, can tell us the equilibrium state of the system, whether or not a spontaneous process could occur in the forward or the reverse direction, and we're going to see some formulas that relate spontaneity to equilibrium constants. We're going to bring some of those back up, but no ice tables, I swear. Well, I can't think of any ice tables, so I don't think there's any. And kinetics tells us things about the practicality of a reaction and the pathway of the reaction. What the steps, the elemental steps of the reaction are, the mechanism. And remember, we did a bit of that work when we covered kinetics. And as we mentioned just a moment ago, the gasoline doesn't typically burn unless we throw a spark in there. That's because there's a relatively high activation energy for that reaction, which is a good thing since we are made of combustible material and there's oxygen all around us and inside us. But luckily, we're relatively cool and we don't spontaneously combust. So to give us a sense of whether or not we're on the right track, understanding spontaneous or non-spontaneous, pause the video for a second, look at all four of those and tell me whether or not they are going to be spontaneous or non-spontaneous processes. Pause and try that. Did you pause? Maybe you did. If you did, you're good. If you didn't, you're naughty. But I'll ask you about those next time. But you ought to be able to tell me. In the early days when thermodynamics was an infant branch of science, and the chemists and physicists were kicking around some of these ideas, their first inclination was that a spontaneous process is one, like a combustion reaction, that is decreasing in energy. In other words, it's exothermic. Its enthalpy change is a negative value. And it is very true that most exothermic processes are spontaneous. They can occur without any outside influence on the system. And we do know that lots and lots of endothermic reactions are non-spontaneous. We human beings and other living things are very non-spontaneous in our biochemistry. A lot of the reactions we do are endothermic reactions, and yet they happen, clearly, because we're alive. So exothermic processes are generally spontaneous, and endothermic processes sometimes are not, but that's not the whole explanation, because there are exothermic processes that don't happen spontaneously, and there are endothermic processes that do. Ice melting at a temperature above 0 degrees C at 1 atmosphere is a spontaneous process, but it is also endothermic. So clearly, spontaneous and endothermic are not mutually exclusive. And this is a slide showing that same idea. Reactions like the combination of hydrogen and oxygen, the elemental forms, to produce water. That reaction is quite spontaneous. Just give it a little spark and it will go like mad. And that process is very exothermic, 286 kilojoules per mole of water produced, 286 kilojoules of energy released. But water vaporizing from liquid to a gas, evaporating, is clearly an endothermic process because the water vapor has more energy than the liquid it came from. But that process happens spontaneously. Spill some water, on the floor and come back tomorrow and it's gone. So what's going on? Well, we got to come in to the concept of entropy now to explain these spontaneous and endothermic processes. And here's a phenomenon that we are all very familiar with, that if we have a substance in a high concentration in one space, and we allow that substance to move around freely, then it spreads out, it diffuses. So in the diagram here we have a flask that has a valve between the two bulbs and two different gases separated by the closed valve. If we open the valve, those gases will mix. In a very short time, we'll have equal concentrations of both. Well, there's no heat change in this reaction, at least nothing significant. And there are no changes in intermolecular forces. If we choose the molecules carefully, there will be no real increase in attractive or repulsive forces. So why do the gases mix? Why do they spread out? There has to be an explanation for this, and there is, and the explanation is entropy. Entropy is, apart from enthalpy, another one of these things that drives spontaneous processes. The entropy of the universe is constantly increasing. Now, what is entropy? It is a rather funny, quirky mathematical concept, and it is tough to really portray. And I think your textbook does a pretty good job of this mathematically to show why the phenomenon that we're seeing in this diagram, where we have the bulb on the left side filled with gas, a closed valve separating it from an empty bulb, and when we open that valve, the gas spreads equally between the two bulbs. And there's some good diagrams in your textbook that describe this phenomenon. I think it will help you if you're struggling after this video lecture to maybe go through a couple of those pages at the beginning of chapter 17 and see if the added mathematical explanation will help you out. And the math isn't too ugly. They're using mainly fractions and stuff to show these processes. So again, the total energy of the system remains relatively unchanged when we allow the gas to move from the one side and spread out throughout the entire volume of both of the bulbs of that container. The total energy is the same, but the number of different possibilities for the distribution of those energies, and we're talking mainly the motional energy, the moving energy of those particles. And that physical force is the law of thermodynamics that says the entropy of the universe will increase. And entropy is the total number of different distributions of energies in a system. And if I have all of the molecules on one side of this bulb, the total number of arrangements of those molecules and the kinetic energies that they possess is limited to the space that they fill in this bulb. If I provide them a greater volume to occupy, there are now a greater number of possibilities for those molecules to distribute themselves and their energies throughout the entire volume of both bulbs. So the entropy of the system has increased, and that's what drives those molecules to spread out into those empty spaces. This is showing you a similar idea, and intuitively we know that if we take two liquids and mix them together, they tend to form a continuous and rather homogeneous mixture depending on the chemical nature of the liquids. But if it's two soluble substances, two miscible liquids like benzene and toluene, when we pour them together, they mix perfectly randomly and evenly. We don't get a layer of one and the other. And that's because, again, the entropy of the system on the right is much greater. The number of different possible energy distributions is greater when there's a random assortment of the molecules rather than when all of the toluene is on one side and all of the benzene is on the other side of the beaker. Same thing is happening when we change a phase from solid to liquid to a gas. We increase entropy with each step. Liquid particles can move around with some freedom, so they can rearrange themselves into different distributions of their energy. And the liquids have greater entropy than the solids, where the particles are locked into place. And then the gases have a much greater entropy than either the solid or the liquid, because now the particles are flying around with a much greater propensity to spread themselves out into different distributions. And the fact that in the gas phase they tend to be much, much further apart is another reason that there's greater entropy. So I'm going to just have you pause these last couple of videos, read the ideas, because I don't want to make this too long, and try the practice problems. So I think I spelled out these things the way I wanted to. Go back and look at the last slide, and this one, again, if you need to, and then see if you can answer the questions here and the questions here. And I'll see you in class.